Section 2 is a little bit more challenging for you, I believe, but it's gonna be more fun, okay? I guarantee you. Okay, multi-stage experiments and modeling games. So we're gonna have a lot of real-world situation there, and you know, we're gonna have some fun games there too. So let's see. Okay, here's one experiment we're gonna do. Okay, we will consider two-stage experiments. You can always have more than two stages. Of course, when you increase the stages, it gets harder. So let's start from two stages there. For example, a ball is drawn from a box and its color is recorded. The ball is then replaced. Do you see I highlighted there because it's very important whether you replace it or you don't replace it. It matters, okay? So in this case, in this experiment, we're gonna put it back. Once you draw a ball, you're gonna put it back. So we have the same number there, right? So let's consider in this box you have three balls, red, white, and green. So here I made a table for you for your convenience. So this is the first row. You can have red, white, and green. Because you put it back, you still have red, white, and green. It didn't change, right? Here, first row and second row, what color is my first row and what color is my second row really matters, right? So we are going to fill the table up. And I will ask you guys to do the same thing there too, okay? So on your notebook, I want you to draw that table. I will do that too. My handwriting is not perfect here. I'm still getting used to, using this one. This is one way to record what you have, okay, what you drew. So you can think about this as the first row. Let's save it. Okay, sorry about that, guys. Okay, now this is the first row and this is the second row. So you can have, theoretically, you can have red as the first draw, right? And for the second row, because you put it back, red is still there, you can still have red. So you can record it. If you have red as the first row, you can have not only red, but you can also have white as the second row. Let's say you have red as the first row, you can have green as the second row. So when you're looking at this kind of a coordination, you can say, oh, this is the first row, this is the first row, and this is the second row. So you can read easily. First row is red, second row is white, first is red, second is green, and you can go systematically. You are done with the first row as red. You can also have first draw as white color, but you can have second color as red. With the first white, second can be white too, because you put it back. First color can be white, but second color you can have it as green, right? So when you're continuing doing that, you can complete this one and you can see all the possible outcomes there, and we can call that as sample space. Yes. So this is your sample space when you have the experiment of a ball, drawing ball twice by replacing them, right? Okay, so we got all the outcomes. So from here, let's find the probabilities. Let's find the probabilities of obtaining GR. So find GR. Where is GR? GR is right there, right? Is there any other GR? We have RG, but that's different from GR because GR means you drew G green at the first row and red at the second row. That's different from first row's red and second row's green. So obtaining GR is only one out of this total. How many outcomes are there? 9, 3 by 3, right? So 1/9 is the probability for obtaining GR. That's part A. How about part B? Obtaining either GR or RG. Are they mutually exclusive? Yes, because it doesn't happen at the same time. It's either this or that. So you can add the probability of GR, which is 1/9, and probability of getting RG, which is also 1/9. So you have 2/9, right? Okay, how about part C? Obtaining R on the second row. So take a look at all the R's on the second row. This is a second row. So all the R's on the second row are only these 3 cases, right? Other things, these are all different colors for the second row. So we know there are 3 out of 9 total. You can simplify that because both numerator and denominator are divisible by 3. So divide both by 3. 3 times 1 is 3. 3 times 3 is 9. So you have 1/3. I guess it makes sense for you. Okay. We also want to talk about the tree diagram here. So think about all the possibility and all the probability. Okay, so think about first row. First row can be red, white, or green. And the chances for each is the same, right? So you can have 1/3, 1/3, and 1/3 for the first row. So the total is 3/3, 1. So it makes sense, right? From there, second row, well, first row doesn't matter, right? It doesn't affect the second row. So you still have red, white, green. For the first row is red, and same for white. You can still have red, white, green. For the green too, red, white, green can happen for the second row. So you can continue to do that, and these are all the outcomes that we drew up here in the table. It's exactly the same thing. Okay, so 9 outcomes are the ones that you have, right? So take a look at this. The probability to get red from here is also 1/3. To get white in the second row is 1/3, and green is 1/3. So getting RR is 1/3 times 1/3, which is 1/9. Right? That's what we found there too. Probability of red and white. Red is 1/3, white is 1/3, and they don't affect each other, so you can just multiply them to get 1/9. Same for these. You see that 1/9 is coming from 1/3 times 1/3 to get 1/9. 1/3 times 1/3 is 1/9. So you can see that, right? And tree diagram is very, very helpful, so I strongly encourage you to use that, and we will use that too rather than using this kind of table. Okay. Oh, it's asking me to pay more. We can always erase this. So let's continue this one anyways. Okay, a box contains 1 black ball and 2 white balls. If a ball is drawn at random and the color recorded, a tree diagram for the experiment might look like this. I am not gonna show you yet. Pause the video and I want you to draw your own tree diagram that reflects this work. In the meantime, let me erase this. Okay. And we can reuse it. The tree diagram for that. Hopefully you did successfully. And let's look at this together. Okay, so Okay, let me start from here. A box contains one black ball. Okay, I will just write it as one black, two white ball. You can always draw, two black balls and one, I'm sorry, one black ball and two white balls. So in a box you have these, right? Okay, if a ball is drawn at random and the color is recorded, let's draw the tree diagram for that. Okay, so you can either have black ball or white ball, because we are drawing only ones, right? And what's the probability to get one black ball? There are total 3, but there's only one black ball. So to get black ball, you have a probability of 1/3, right? How about getting white balls? Since there are 2 white balls and the total 3, this is the probability to get white ball. So when you add these two together, you can have 3/3. That's how you check, right? Okay, so that's the tree diagram we can have. Okay, and if you are using ordered pair, you can have a black black, black white, white black, white white. You can do that. In probability, it's the same thing. We already talked about it, so I will skip it. And let's think about rolling a pair of dice and finding sum. So I already marked it here for you. So first roll of the die, you can have 1 all the way to 6. The second roll, you can have 1 to 6. So if we record it here, the first number represents the first roll, second number represents the second roll. So if both are both number that appeared on your rolling die is 1, then you can record it as 1 1. So pick any number. This means first roll you got 4 and the second roll we got 3. So you understand that now, right? So all the possible outcomes are here in these boxes. So sample space is there, and how many outcomes are there? 6 by 6. There are 36 outcomes, right? You can also, if you have time, you can draw all the possible outcomes. This is exactly same as, this one with 1 1, 1 2, 1 3, and so on. So we can stop there. What I want to do is finding sum, because the question was asking finding the sum, right? Roll a pair of dice and find the sum. So this is the outcome you can have, but that's not what we're concerned about. So you need to actually add these two numbers and find the sum there. So in this place, instead of that, you can say 2, because 2 is the sum. And you can have 3 as the sum, and 4 as the sum, 4 as the sum, 5 as sum, 6, 7. Add all of these two numbers together. So 3, 4, 5, 6, 7, 8, 4, 5, 6, and so on. So you can have this, because this is the sum between 1 and 1, that's 2, 1 and 2, together it's 3, 1 and 3, 4. So you can interpret that. So when you have a 6 and 6, that's 12. So these are the outcomes. 2 as a sum occurs only once. So we get to know the probability of getting 2 as a sum is only 1 out of 36. 12 for the same thing. But to get 3 as the sum, you have 136 here and 136 there. So there are 236 of a probability. Of course, you can simplify that, right? So probabilities to get 2 as a sum, you have only 1 time out of 36. Same for 12. But to get 3, there are 2 36th. To get 4, you have 3 36th. You can see the pattern there, right? To get 5, we have there's a mistake. It's supposed to be slash there. Okay, So 4 out of 36. To get 6, 5 out of 36. To get 7 is the sum, 6 out of 36. Then it decreases. So it's kind of symmetry. It is a symmetry on around this 7. So these two are same, these two are same, and that two are same, two are same. So you can see that, right? Okay, so when you add these numbers together, the probabilities all together, it's gonna be 36 out of 36. So you get 1 as the maximum, right? So you can always check your answer by adding them together to get 1. Now let's talk about independent events. Independent events is different from mutually exclusive. So independent means independent when the occurrence of one event has no influence on the outcome of a second event. So when you're thinking back to our example, when I replaced the ball in the box, it didn't make any change to the second draw, right? So first draw and second draw are independent when you replace the ball. But if you don't replace the ball, it does make an influence to the second draw, right? Then they are not independent, they are dependent. Okay, so in the context, you can already get to know whether it is independent or dependent. So here's one example. Let's suppose you are flipping 2 coins. Event E1 is obtaining a head on the first coin. And think about you are flipping that coin second time. Does first outcome make an influence on the second one? No, it doesn't, right? So they are independent events. So you can have head, tail, head, or tail. Okay, these are all the possible outcomes. So we call that as sample space. Probability to get head is only 1 time out of 4, so 1/4. To get tail, it's only 1, right? 1 out of 4. But how about getting 1 head or 1 tail? Doesn't matter with the order. So we have 1 head and 1 tail, 1 head and 1 tail. So 2 cases there. So it's 2 out of 4. So probability to get 1 head and 1 tail, it should be 2/4, or simplify that as 1/2. Consider now 2 boxes. Box 1 contains 2 white balls and 2 black balls, and box 2 contains 2 white balls and 3 black balls. Let B1 be the event of drawing a black ball from box 1, and B2 is the event of drawing a black ball from box 2. Have some time, okay? And suppose a ball is drawn from each box, and we are interested in the probability that each ball is black. So, probability of B1 and B2. Think about it, B1 and B2. What I get from B1 affects any outcome of B2? No, it doesn't, right? So they are independent. So you can just have probability of B1 and probability of B2, right? So what's the probability of getting B1? So getting black ball from box 1. There are 2 black balls out of 4 total, so 2/4 or 1/2. How about here, getting black ball from box 2? You have 3 black balls out of total 5. So it's gonna be, yes, 3/5. Right? Then consider the probability of getting both black balls. So you can multiply these 2 outcomes because they are independent. So when they are independent, to get both, you can multiply those probabilities. Okay, so you have 2/4 times 3/4, which is 6/20, or 1/2 times 3/5, that's 3/10. Or you can go from here and simplify by dividing both numerator and denominator by 2 to get 3/10. Okay, so remember, to get probability of intersection for independent event, you can just multiply probability of B1 by probability of B2. Okay. Okay. How about we pause here for replacement and we will come back later.